Very good morning to all. Second part of Electrochemistry in Physical Chemistry, Chapter 2. Explanation of the amorphous behavior of a strong electrolyte, intrinsic effect, Debye-Huckel theory. The increase of equivalent conductance with dilution in case of weak electrolyte can be easily explained on the basis of Arrhenius theory, which suggests that the conductance increased because the dissociation of the weak electrolyte increased with dilution. However, in case of strong electrolyte, as they are almost completely dissociation even at moderate concentration, the increase in equivalent or molar conductance with dilution must be due to some other factors. The qualitative explanation put forward is as follows. The conductance of the solutions of the electrolyte depend not only upon the number of ions but also upon their speed. In case of a weak electrolyte, the increase in conductance with dilution is due to the increase in dissociation of electrolyte. Due to increase in number of ions, the speed of ions in this case are not much affected by change in concentration because the number of ions produced is so small that distance between them quite large, so that there is no interference in the movement of ions by the other ions. However, in case of a strong electrolyte, the number of ions produced on dissociation is so large that the freedom of movement of ions is hindered by the other ions present around it. When the solution is dilute, the ion interference decreases and hence ion speed increases, and so does the equivalent or molar conductance. The first successful attempt to explain the various of equivalent or molar conductance of strong electrolytes with dilution qualitative was made by Debye and Huckel 1923. The fundamental idea underlying to their work is that because of electrical attraction among the oppositely charged ions, each ion is surrounded by a large number of oppositely charged ions, which may be regarded as an ionic atmosphere of opposite charge, and this affects the number of ions in an electric field. The electrical attraction among the oppositely charged ions will affect the number of ions in the electric field are called electronic effect. There are two such effects which are briefly described below: relaxation effect or asymmetric effect. In this solution, each ion is surrounded by the ionic atmosphere of opposite charge so long as no field effect is applied. The ionic atmosphere remains symmetric around the central ions. However, when a current is passed through the solution, the central ions moves toward the oppositely charged electrode. As it is moving out of the ionic atmosphere, it had to rebuild in ionic atmosphere of opposite charge around it, and the old ionic atmosphere die out. However, neither the destruction of old ions atmosphere nor the formation of ionic atmosphere take place instantaneously. Each of them takes some time called the time of relaxation. During the time, the old ionic atmosphere pulls the moving ion backward and hence retards its motion. Hence, this effect is called relaxation effect. Alternately, it may be agreed that as the central ion moves, the symmetry of the ion atmosphere is lost. More ions of the ionic atmosphere are left behind them are present on front. The excess ion of the ionic atmosphere present behind the moving ion drag the ion backward and retard ion motion. Thus, the effect arises because of the asymmetry of ionic atmosphere of the moving ion, and hence is also called asymmetric effect. Electroph- Electrophoric effect. When EMF is applied, the central ion moving in one direction and the oppositively charged ion atmosphere move in opposite direction. As the ionic atmosphere moves, the solvent moving attack to it take place in the direction opposite to that of a movement of the central ion. In other words, the central ion is moving against the stream, hence its motion is retarded. This effect is called electrophoretic effect. Since it is similar to the opposite, the movement of colloidal particle in an electrical field. Besides the above two effects, the third retarding force is the normal fractionally resistance offered by the medium, which depends on the viscosity of a medium, its dielectric constant etc. Based upon the above idea, Debye and Hooker 1923 derived a mathematical expression for the variance of molar conductance with concentration. This equation was further improved by Onsager, and now the equation is called Debye-Hooker's Onsager equation, or simply Onsager equation. For a univalent electrolyte, it can be written from lambda m is equal to lambda naught m minus bracket 82.4 upon dt की power half n plus 8.20 into 10 की power 5 upon dt की power 3 upon 2 lambda naught m bracket बंद into root c. First equation. Delta Cm is equal to molar concentration at concentration C. Delta naught M molar concentrations at infinite dilution. D is equal to dielectric constant of the medium N. Coefficient N is equal to coefficient of viscosity of the medium. T is equal to temperature of a solvent in degree absolute. C is equal to concentration of the solution in moles per liter. As D and N are constant for a particular solvent, therefore at constant temperature, the above equation can be written in the form molar concentration at concentration C is equal to molar concentration at infinity dilution minus bracket A plus B molar concentration at infinity dilution bracket band into root C, where A and B are constant for a particular solvent at a particular temperature. Variation of the Onsager equation. Two tests can be readily performed to verify the Onsager equation. These are the float of a lambda m versus root c should be linear. The slope of a line should be equal to a plus b lambda naught m calculated by the substitution value of a variation constant directly. The float of a lambda m versus root c for some common univalent electrolyte dissolved in water at 25 degrees Celsius. The lines represent theoretically slopes, where small circles represent the experimentally observed point. Thus, the agreement is very fair. In case of a curtain salt like NaCl, KCl, it is observed that the agreement is excellent at low concentration, but at appreciable concentration, the measurement conductance are somewhat higher than those calculated from Onsager equation. It is probably because there may be some other retarded force which have been neglected. Thus, the anomaly of strong electrolyte is not yet fully resolved. From equation second, it may be seen that at infinite dilution, where C approximately 0, lambda m becomes equal to lambda naught m as abstract signify of a Debye-Hooker theory. The significance of a Debye-Hooker theory object lies in fact that it is able to explain why the molar conductance of a strong electrolyte at any concentration is less than the limiting value of a lambda naught m at infinite dilution. In fact, the complete ionization of the strong electrolyte. Migration of the ions and transport numbers. Migration of ions. When electricity is passed through the solution of electrolyte, this ion present in solution are liberatory at the electrolysis occur. This movement of ion toward the oppositely charged electrode is called migration of ion. That ions actually exist independently and move with the passage of a current in solution toward the oppositely charged electrode can be seen experimentally as follows. Take a U-tube Fill the lower portion of by CuCr2O7 jelly obtained by mixing a 5% solution of agar-agar and a mixture of CuSO4 and K2Cr2O7 and allow it to set. The jelly is green in color. To mark position of jelly, some charcoal is cracked over the green jelly. Over charcoal is both the limbs is added KNO3 solution in agar-agar, KNO3 jelly and the them aqueous solution of KNO3. When current is passed, blue color Cu2 plus ion are seen moving toward negative electrode and yellow color Cr2O7 to negative ions are seen moving toward positive electrode. After some time, the two types of ions are seen moving with well-defined boundaries. The experiment clearly shows the migration of ions. Migration velocity of ions and change in concentration heteroscophical device. According to Faraday's second law of electrolysis, when the same quantity of electrolytes passed through solution of different electrolytes, the ions are always liberated in equivalent amount. This, however, does not necessarily mean that the ions move with the same speed. It may be illustrated as follows. Consider a cell containing the solution and provide with the anodes A and cathode C. Let the solution lying between the electrodes A and C be divided into the three compartments, anodic, middle and cathodic. With the help of imaginary portions, partitions A and C. Before electrolysis for there are three pairs of ions. Positive sign indicate the cation, negative signs anions, four being present in each of the anodic and cathodic compartment and five in the middle positions. Now the following different cases may be considered. Anodic compartment A, four signs, central compartment have five signs positive and negative, cathodic compartment have four positive negative sign. Case 1. When only anions negative moves. Let two anions leave the cathodic compartment and enter anodic compartment. We get the position second. Although the cations have not moved still, we see that number of ions liberated in same by 2 at both the electrodes, but we see that concentration in anodic chamber has not altered while that is cathodic chamber has fallen by 2 molecules. Similarly, we can show that cations are capable of movement and two of them enter cathodic compartment from anodic compartment. When them there will be a fall in concentration of two molecules in the anodic chamber. Thus, we see that the velocity of an ionic is proportional to the fall of concentration of chamber from where it lived. Case second, when cation and anion move at the same rate. Let us assume that two cations move from the anodic compartment to the cathodic compartment and two anions move from the cathodic compartment to the anodic compartment. Then we get position 3. In this case, there is fall in concentration of a two molecule in each compartment, but we find that the number of ions liberated at both the electrodes is same. Case third. When the cation move at double the speed of an anion, suppose that two number of a cation from anodic compartment leaves and enter the cathodic compartment. Since the speed of an anion is half the speed of a cation, therefore only one anion enter the anodic compartment. The position is shown 4. We also observe that the fall in concentration in anodic and cathodic compartment are 2 and 1 molecule respectively. The number of ions discharged in again the same wise 3 on each electrode. Conclusions. From the above illustrations, we draw to the following conclusion. First, fall in concentration around any electrodes directly proportional the speed of the moving away from it. It means fall in concentration around cathode directly proportional speed of the anions UA, and fall of concentration around cathode directly proportional speed of cation UC. Fall in concentration around anode upon fall in concentration around cathode is equal to speed of cation upon speed of anion. Irrespective of the speed of the ion, the number of ions liberated on the both the electrode is equal. Instead of the number of ions, we can speak of the number of gram equivalent of the ion deposited on the electrode, depending upon the number of Faraday of electricity passed. Case 4. When the electrodes are attackable. The above relationships had been derived on the assumption that the ions do not react with the electrode, but in a silver voltammeter containing AgNO3 solution and having silver electrodes, each NO3 negative ion that reach the anodic compartment react with Ag of the electrode, forming AgNO3 and instead of decrease. There is an increase of concentration in the anodic compartment in a silver voltmeter. The above three cases are shown in figures. It is seen that in every case there is always an increase in concentration in the anodic compartment. The increase in concentration takes place even when the Ag positive ion migrates from the anodic compartment to the cathodic compartment. In order to find the increase in concentration, the would have taken place if a number Ag positive ion had migrated from the anodic compartment to the cathodic compartment. A silver or a copper voltmeter, also called coulometer, in place read. For the number of a gram equivalent of Ag or Cu deposit in this voltmeter is X. Obviously, X gram equivalent would have been the increase in the concentration of anodic compartment if number Ag positives ion had migration from the compartment. However, the actual increase in less due to migration of Ag positive ions. For the actual increase in the concentration of Ag in the anodic compartment is 5 gram equivalent. Hence, fall in concentration in the anodic compartment due to migration of Ag positive ions or is equal to X minus 5 gram equivalent. Further from it may be seen that fall in concentration around cathode is equal to increase in concentration around anode by gram equivalent. Thus, the speed ratio in the case will be given by speed of Ag positive ions upon speed of NO3 negative ion is equal to X minus Y upon Y. Transport number as seen in sections when an electric current is passed, the ion migrate toward the electrode. Thus, the electric current is carried by ions. Each ion carries a defined fraction of the total current depending upon its speed. The fraction of the total current carried by an ion is called the transport number or transference number or hit-off number. Greater the speed of an ion, greater the amount of a current it will carry with it, hence greater will be its transport number. Let UA and UC be the speed of anion and the cation respectively. Current carried by the anion directly proportional UA is equal to KUA. Current carried by the cation directly proportional UC is equal to KUC. Since current is carried only by ions, total current carried is equal to current carried by anion plus current carried by cation. KUA plus KUC is equal to K bracket UA plus UC bracket 1. Transport number of anion N is equal to KUA upon में KUA plus KUC. N is equal to UA upon UA plus UC. Similarly, transport number of cation will be NC is equal to UC upon UA plus UC. Two important relationships Na plus Nc is equal to UA upon UA plus UC plus UC upon UA plus UC. Them is equal to UA plus UC upon UA plus UC is equal to 1 or Na plus Nc is equal to 1. Sum of transport number of anion cation of electrolyte is always unity. thus no current is lost of any other function and the whole current is carried by the ions. N is equal to UA upon में UA plus UC is equal to 1 upon में 1 plus में UC upon UA is equal to 1 upon में 1 plus R, where R is equal to UC upon UA, speed of a ratio of the cation of the anion. Similarly, Nc is equal to R upon में 1 plus R, thus N is equal to UA upon में UA plus UC is equal to 1 upon में 1 plus R. Nc is equal to UC upon UA plus UC is equal to R upon में 1 plus R. Determination of a transport number. There are a number of a method for the determination of a transport number. First, Ethoff method. Second, Lodage moving boundary method. Third, EMF method. Out of these, the first two methods are described below. First, Hitov methods. Principle. The method is based upon the principle that the fall in concentration around an electrode is proportionally to the speed of ion moving away from it. Fall in concentration around cathode upon fall in concentration around anode is equal to speed of anion upon speed of cation. Adding 1 in both sides, we get UA upon UC plus A. UA plus fall in concentration around anode plus fall around cathode upon fall in concentration around anode is equal to UA plus UC upon UC. Fall in concentrations around anode upon total fall in concentration around both the electrode is equal to UC upon UA plus UC by the reciprocal sum. If the concentrations are expressed in terms of gram equivalent, the above expression may be written as Nc is equal to number of gram equivalent lost from anodic compartment, number of gram equivalent lost from the both the compartment. Refreshing, it may be seen that the number of gram equivalent lost from the both compartments is equal to the number of gram equivalent discharged in each electrode. This turn can be found by the placing a silver or copper voltmeters in series, as according to Faraday's second law, when the same quantity of electricity flow through the silver or copper voltmeter, the same number of gram equivalent of Ag or Cu will be deposited. Thus, the above formula reduced to Nc, number of gram equivalent lost from the anodic compartment upon the number of gram equivalent deposited in the voltmeter. Thus, the determination of the transport number of cations involved to the determination of the number of gram equivalent lost from the anodic compartment and the number of gram equivalent of Ag or Cu deposited in the voltmeter placed in series with the appraised. However, it is important to note that the above result is applicable only when the electrodes are non-attackable by the ion. If the electrodes are attacked, the result is calculated in different manner as discussed in the calculation at the end of the section. To determine the transport number of an anion, there is no need to find the loss in concentration of the cathodic compartment because Na can be calculated directly from the equation Na is equal to 1 minus Nc. Appraised. Evidently, the operation should be such that it should consist of their compartment, namely the anodic, the cathodic and the central compartment. The solution of the three compartments should not mix with each other on electrolysis. If should be possible to taken out the sugar of any compartment without disturbing the solution of other compartment. The above requirements are met in the apparatus shown in. It consists of U-tube joined on its two sides to two vertical bulbous glass tubes. All the three U-tube and the two vertical tubes have got the stove cocks at their bottom. The U-tube is also provided with two stove cocks, one on either side at the top, so as to cut off the various compartments from each other when required. In the two vertical tubes are placed the anodic and cathodic separately. These are platinums if it accepts the anode. It is desire that these should not be attacked by the anion. Alternatively, the anode and the cathode of a silver or a copper are taken depending upon the weather transport number of Ag positive ions or Cu negative positive ion is to be determined, in which case the anode is attacked by the ions and the aperture is connected to a silver or copper voltmeter, also called coulometer, in series with the aperture together with a battery, restore a key and the milliammeters as shown. Procedure: the aperture is filled with the solution of a electrolyte. The transport number of a whose ion is to be determined. A silver or copper voltmeter is placed in series with the apparatus and the various concentration connections made by show. Before electrolysis, the concentration of the electrolyte is found by the titration a known weight of the solution against two suitable reagent. Now a current of a 0.01 to 0.02 ampere is passed for 2-3 hours. A low current is used so that the change in concentration around the electrode is not too high, as otherwise the diffusion may take place. After electrolysis, the solution from the anodic compartment is taken out, winged and titrated as before to know the amount of the electrolyte present. The weight of the silver deposit in the silver voltmeters is also determined. The solution from the central compartment is also taken out and titrated to see that there is no change in concentration. In case a change in concentration is observed, the experiment is repeated. It is important to note that in this measurement, the weight of the solution are taken instead of volumes. This is necessary because after electrolysis, the density of the solution changes and so does the volume. Calculation: the method of calculation may be illustrated by taking the example of AgNO3 as the electrolyte and using silver voltmeter in series. When the electrodes are not attacked, when platinum electrodes are used after electrolysis for the weight of the anodic solution take out W1G, weight of AgNO3 found to be present by titration is equal to W2 gram. Weight of water present is equal to W1 minus W2 grams, thus W1 minus W2 gram of water contain W2 gram of AgNO3 after electrolyte in term of a gram equivalent. With W2 gram of AgNO3 is equal to W2 1 upon 70 gram equivalent of AgNO3, W2 is equal to W2 upon 170 gram equivalent of Ag can be write is equal to X gram equivalent C. Hence, we can say that after electrolysis, W1 minus W2 gram of water contain X gram equivalent of Ag. Before electrolysis, for W3 gram of solution contain W4 gram of AgNO3. Weight of water present is equal to W3 minus W4 gram. W3 minus W4 gram of water contain W4 gram of AgNO3 before electrolysis. W1 gram minus W2 gram of water will contain is equal to W4 upon W3 minus W4 into W1 minus W2 gram of AgNO4 and change in the equivalent gram. Then find W4 upon W3 minus W4 into W1 minus W2 upon 170 gram equivalent of Ag can be say is equal to Y gram equivalent. When the electrodes are non-attacked, X less than the Y, fall in concentration of anodic compartment, Y is equal to Y minus X gram equivalent of Ag. Suppose the weight of silver deposit in silver voltmeter Wg is equal to W upon 180 gram equivalent of Ag is equal to Z gram equivalent C. Transport number of Ag positive ion and Ag positive fall in concentration around anode in gram equivalent upon amount of Ag deposit in voltmeter in gram equivalent is equal to Y minus X upon measure. transport number of NO3 negative ions NO3 negative is equal to 1 minus Nag positive. When the electrodes are attacked, when silver electrodes are used. In this case, as the NO3 negative ions reach the anode attacked the silver anodes, there is increase in the concentration of Ag positive ions in the anodic solutions. In this case, we will have X greater than Y. Increase in the concentration of the anodic solution X minus Y is equal to X minus Y gram equivalent of Ag. This is increase in the concentration take place in spite of the migration of Ag positive ions from the anodic compartment to the cathodic compartment. If a number of Ag positive ions had migrated from the anodic compartment, the increase in the concentration of Ag positive ions in the anodic compartment would have been higher and equal to Z gram equivalent of Ag. Hence, fall in concentration in the anodic solution due to migration of Ag positive ion is equal to Z minus bracket X minus Y gram equivalent of Ag. Transport number of Ag ions Z is equal to Z minus X minus Y upon Z. Transport number of NO3 ions is equal to N minus Nag plus. In case of a copper voltmeter is used, the number of gram equivalent of copper deposit in the voltmeter is obtained by dividing the weight of copper deposit Wg by the equivalent mass Y. Formula: transport number of a cation Nc is equal to fall in concentration around anode upon the total fall in concentration in both the compartment, or transport number of cations is equal to number of a gram equivalent lost from the anodic compartment upon the number of gram equivalent of Ag or Cu deposit in voltmeters or kilometer connected in series. Moving boundary methods. This method is based upon the fact that the transport number of a cation and anions are given by Nc is equal to Uc upon Uc plus Ua and Na is equal to Ua upon Uc plus Ua. Thus, by determining the speed of cation and the anion, the transport number can be calculated. The process used is shown in figure. It consists of a long tube mounted vertically and fitted with the platinum electrode on two sides as shown. The salt Ba under investigations is made into solution and then placed between the solution of two other salts B-A and B-A, one having a common cation and other having common anion. For example, if Ba is KCl, B-A may be LiCl and Ba- may be CH3COOK. The three solutions are arranged in order of increasing density downward to avoid mixing effect. The original boundaries are A and B. Even if the solutions are colorless, the boundaries can be observed because of the difference in the refractive index of the solution. In other that the boundaries may remain sharp throughout the experiment. B and A must be smaller velocities than B and A respectively, so that B does not overtake B and A does not overtake A. When the current is passed, the boundaries move to A and B. Thus, speed of cation B positive, Uc directly proportional, length A, speed of anion A negative, Ua directly proportional, length B. Hence, Nc is equal to A upon A plus B and Na is equal to B upon A plus B. Factor on which transport number depend. It has been stated earlier that the transport number of an anion is directly proportional to the speed of the anion, which is turn depend upon a number of factors. Examples: nature of ion. Normally, the smaller the size of the ion, greater is the speed and hence higher in its transport number. For example, the transport number of H positive ions in 0.1 and NCl, normality NCl is greater than that of ions is Na positive ion in 0.1 normality NaCl or K positive ion in 0.1 normality KCl, etc. Second, nature of a other ion present. For example, the transport number of a Cl negative ions NCl negative in HCl is different from that of Cl negative ions in NaCl. This may be explained as follows. NCl negative in HCl is equal to UCl negative upon में UH positive plus UCl negative, first equation. NCl negative in NaCl is equal to UCl negative upon U Na positive plus में UCl negative, second equation. Where U plus H plus comma UNA plus and UCl negative represent the speed of H positive ions comma N positive and Cl positive Cl negative ions respectively in their respective solution. As Na positive ions is larger in size than the N positive ions, UH positive greater than UNA negative as a result the denominator of expressions. First in greater that of expression, second hence NCl negative in NCl is smaller than NCl negative in NaCl as the numerator is the same in both in case. Third, hydration of the ions. The speed of an ions and hence its transport number is very much affected by the hydration of a ions. For example, lithium positive ions are smaller in size of Na positive ions and hence may be expected to have higher transport number than Na positive ions, but the actual position is otherwise. This is because lithium positive ions are more hydrated than sodium positive ions. Similarly, sodium positive ions have a smaller transport number than potassium positive ions. Concentration. The transport numbers of a ion change with concentration, but the change is very small. However, in case the increase in concentration it results into the formation of a complex ion, the transport number changes significantly. For example, the transport number of a Cd2 plus ion in cadmium iodine solution falls from 0.444 in 0.005 million solution to 0.03 in 0.025 molar solution. At still higher concentration, the transport number appears to be zero or even negative. This is explained on the basis of formation of a complex CdI2 I4 negative ions at higher concentration follow. CdI2 arrow Cd2 plus aqueous plus 2I aqueous, Cd2 positive aqueous plus 4I negative aqueous arrow CdI4 2 negative aqueous. In dilute solution, there are very few CdI4 2 negative ions, so that Cd2 plus ions show their normal transport number. However, as the concentration is increased, more and more of CdI4 2 negative ions are formed, which migrate to the anodic compartment. A stage convection and many CdI4 2 negative ions migrate into the anodic compartment as the number of Cd2 plus ions migrating away from it. Thus, there is no change in the concentration of Cd2 plus ions in the anodic compartment, and so that Cd2 plus ions appear to have zero transport number. Temperatures. As the temperature is increased, the ions tend to approximately a transport number value of 0.5. At this temperature, equal fraction of the current is carried by the cation and the anion. In case of ions having transport number less than 0.5 at ordinary temperature, the transport number increase with increase of temperature. In case of an ion having transport number greater than 0.5 at ordinary temperature, the transport number decrease with increase of temperature. Where the transport number of ions are approximately 0.5 as in KCl. The effect of temperature is very small. Internic effect, how the speed of the ion is affected by the interionic effect has been discussed in sections undergo de Huckel's law. Thank you very much.